Today's lesson is about the atomic structure. You are looking at the book 2. And then in this lesson, we are going to discuss about evidences for the presence of energy levels and sub-energy levels. The lesson we are talking about today is evidences for the presence of electrons in energy levels. And this is done with the help of ionization energy values. Quite a bit of things we had to start studying in this. We'll read this a little bit. There are few evidences for the presence of electrons in different energy levels, sub-energy levels also. But we need to concentrate only one type of evidences known as ionization energy values. Ionization energy values are discussed under two things in our lesson. First one is first ionization energies, and the other one is successive ionization energies. First, let me talk about the first ionization energies. That is first ionization energies. Ionization means the removal of electrons from the outermost energy level of gaseous atoms to change them to gaseous cations. See the points again? There are few important things. What is the ionization? For ionization, the question talks about removal of electrons. From where are we going to remove electrons? Removing of electrons in this ionization energy lesson happens from gaseous atoms. We have to have gaseous atoms. And from gaseous atoms, we have to remove electrons, according to how the note says. And then another thing is this. Most of the time, when we talk about ionization energy, we talk about removal of electrons from 1 mole of gaseous atoms. There should be 1 mole of gaseous atoms. From them, we have to remove electrons. I can give you some examples so that with the examples, we can understand this concept very well. Let me read this first sentence again. Ionization means the removal of electrons from outermost energy level of gaseous atoms to change them to gaseous atoms. For example, I'll take 2 examples. Let me take sodium. If I talk about sodium, according to the definition, there should be sodium gas. 1 mole of sodium gas particles. From them, if you remove 1 mole of electrons, we get sodium plus 1 mole of sodium plus, again, gaseous ions. Similarly, I can talk about oxygen also. Oxygen also must be in gaseous form. And I have not written O2, O. Because if I write O2, it means oxygen molecules. No, I need oxygen atoms. From 1 mole of oxygen atoms, if you remove 1 mole of electrons, you get 1 mole of O plus gas. You may have a question. Most of the time, we talk about oxygen taking 2 electrons to give O2 minus. This is what we know from our O-level lessons because oxygen is group 6 and it needs 2 electrons to get octet configuration, stable octet configuration. So always oxygen takes 2 electrons. No, most of the time oxygen takes 2 electrons. But here I'm talking about an entirely different thing. I'm talking about ionization energy. For ionization energy, we had to spend some energy to form ions, cations, not anions, cations. So for that, we had to remove electrons. So if you want, by providing sufficient energy, we can convert oxygen atoms to oxygen cations as well. So don't get confused here. When it comes to ionization, we can remove electron even from noble gases also by providing enough energy. Now, when we want to remove electrons from different atoms, from sodium or oxygen, how many electrons are not how many, how much of energy is needed. If you want to find out, there are data booklets. We always use data booklets. And a data booklet will definitely show you different ionization energies for different elements. So ionization energy is not equal for different elements. Give me a second. All right. The table over here shows you ionization energy values. This table shows first ionization, second ionization, third ionization, and fourth ionization of different elements. You can see different values are there. However, go to aluminium. Aluminium first ionization energy is 577. Second ionization is 1820. Third ionization is 2740. And next one is 11,000. You may be wondering, what is the meaning of first ionization, second ionization, third ionization, fourth ionization? I talked about removal of 1 mole of electron from 1 mole of gaseous atoms. Actually, this first, second, third ionization means, if I take, just to explain, if I take aluminium gas, from aluminium gas, 1 mole of gaseous atoms, if you remove 1 mole of electrons, you go to aluminium 1 plus gas. If you take this aluminium plus gas to the second line, aluminium plus gas, again giving 1 mole of electrons, you can get aluminium gas. This time it should be 2 plus. And then if you take aluminium 2 plus, still in gaseous form, and remove 1 mole of electrons, you go to aluminium 3 plus, aluminium 3 plus gas. Similarly, I can remove 1 mole of electron from aluminium 3 plus also. Aluminium 3 plus gas, giving 1 mole of electron, aluminium 4 plus gaseous form will be formed. So here, I have given 1, 2, 3, 4 reactions. Because you are removing an electron from the neutral aluminium atoms here, the inner, this is called actually first ionization. And 577 is the energy needed to do this first ionization on 1 mole of gaseous atoms. And second one, you are removing 1 mole of electron from already positively charged gaseous aluminium ions. For the removal of the second electron, we have to give a higher amount of energy. And from aluminium 2 plus, if you remove 1 mole of electron, there we have to spend more energy than for the second ionization. Now I'll draw a line from here. I separated third ionization from the fourth ionization. This is for a reason. Go to the value. Fourth ionization is 11,500. Roughly, this is 600. This is 1,800. This is 2,700. This is 11,600. Quite a big value. The reason is this. When you go on removing electron, you know aluminium is group 3. Group 3 means outermost only 3 electrons are there. You can go on removing the outermost 3 electrons one by one. 1, 2, 3. After you remove aluminium outermost electrons, it gets stable configuration. From the stable configuration, when you remove the next electron, then there's a huge increase in energy value. So likewise, I can take ionization energy values of calcium. So Look at calcium. Calcium is a group 2 element. First ionization energy is 590. Second ionization energy is 1150. Third ionization is nearly 5,000 here. There's a big increase. And then 4,900 to 6,900. When you see a huge difference, the huge difference shows that you are going from one outer energy level into an inner energy level. Let us take another example and observe this feature. I'll take something from, let's say, carbon boron. Boron, first ionization energy is 799. Second ionization is 2,400. Third ionization energy is 3,000. Afterwards, you see 25,000. Huge increase. That shows the moving from one quantum number to another quantum number, or one energy level to another energy level. Likewise, by looking at huge variations in ionization, we can find out where and or when we go from one outer energy level to an inner energy level. This information is really important. We will be using this knowledge in some questions when we start discussing. Okay, now go to this. We use the following to discuss the relative ionization energy values of an atom or an ion. Their effective nuclear charge and shielding effect. Okay, now I should go to this again. Go to something we are very, very familiar with, chlorine. Go to chlorine. Chlorine first ionization energy is 1,260. Sulfur is also in the same period. First ionization energy for sulfur is 1,000. From phosphorus, it is 1,060. What's the meaning of this? From different elements, if you need to remove electrons to make their cations, the amount of energy needed to remove these electrons take different values. Why is it that you see different energy values, so different amounts of energy is needed to remove electrons from atoms? To explain this, we have two terms over here. First one is effective nuclear charge, and the other one is shielding effect. I can explain about effective nuclear charge better when I talk about shielding effect first. So let me go to shielding effect idea first, and then secondly, we go to effective nuclear charge factor. Let me take some examples to talk about the shielding effect. The elements I'm going to use here are lithium, beryllium, boron, and then downwards, below lithium in the periodic table, you have sodium, and below that we have potassium. And if I talk about the period numbers, lithium period is 2, sodium period is 3, potassium period is 4. Please pay attention to this. If I take lithium, I'll write lithium over here. Lithium has 3 electrons. If you organize these 3 electrons around the lithium nucleus, I can write 2 electrons in the first energy level and 1 energy level in the second energy level. And then I go from lithium to beryllium. Beryllium is next to lithium in the periodic table in the period 2. Beryllium also has outermost 2 energy level, outermost 2 electrons. And second energy level, beryllium has 2 electrons. Okay, what is the meaning of the shielding effect now? Shielding effect. shielding effect means this. Lithium has 3 protons. Beryllium has 4 protons. If I talk about the attraction of these 3p protons, 3 positive charge, the outermost electron is attracted towards. I'll increase the size of this a little bit. Okay. When I talk about this electron, which is negatively charged, this electron is attracted to the lithium nucleus because there are 3 protons. So here, electrons are attracted towards the lithium. This is an attractive force. Likewise, here beryllium has 4 protons, so it becomes 4 plus. Charge of 4 plus, because 1 proton is positive 1. We have an electron here. This electron is also attracted. Even though 3 protons are attracting these outermost electrons towards lithium, don't think that this electron is feeling the total attractive force exerted by the 3 protons. You get my point? We have an electron in the second energy level, and the nucleus has 3 protons. These 3 protons are going to attract these outermost electrons towards the nucleus. But remember, the total nuclear attraction due to 3 protons will not be felt by this outermost electron. Why is it? Because inner to this outer electron, there are 2 electrons. These electrons are also negatively charged. What do these electrons do? These electrons always exert an outwards pressure towards its outermost electron. So in addition to the attractive force felt by this electron, outermost electron, due to the nuclear pull, they also experience an outwards force. I'm just trying to give you some figures. Don't get confused with these figures. These are just some numerical values I'm using to explain this concept of shielding effect. If the nuclear attraction on this outermost electron is, let's say, 10 units, I'm just taking some figure, 10 units. Attraction is 10 units. And these 2 electrons are pushing these outer electrons outwards by, let's say, 3 units. 3 units. So what is the net nuclear pull experienced by this outermost energy level electron? 10 inside, 3 outside. The net is 7. Even though the lithium is attracting electrons with 10 units of force, exactly what this outermost electron feel is 7 units. Why not 3? Why not 10? Because 3 units are cancelled by the outwards force exerted by these outermost inner energy levels. Similarly, if you go to the second one, in the second one, there are 4 protons. There are more protons. That's okay. But because of these 4 protons, I'm experiencing an inverse attractive force. Let's say now there are 12 units inside. I'm just giving this value, 12 units. Outwards, what is the force? Outwards force is given by the inner electron. There are 2 electrons. So outwards, there are 3 units. Why there are 3 units? Because in lithium also, inner energy level has 2 electrons. Even beryllium has 2 electrons. So from lithium to beryllium, even though the proton number increases, outwards force is the same because inside 2 electrons are there in each. So what is the force felt by this electron in the outermost energy level? Outwards it is, inwards it is 12. Outwards it is 3. So the net force felt by the outermost electron is 9. Now, my question is this. I'm going to ask a question based on something I have already told. Even though the lithium is attracting the outer electrons with some force, 10 units, it doesn't experience that total attractive force of lithium, because the inner electrons, remember, inner electrons having an outwards repulsive force. That's the reason. Now, this outwards repulsive force is called the shielding effect. It is called shielding effect. That's what we want to discuss. Shielding effect. Now, if somebody asks you, what is the meaning of shielding effect? I can give the meaning of shielding effect in a sentence. Shielding effect is the repulsive force. Shielding effect is a repulsive force on the outermost energy levels, electrons of an atom. Let me read again. Shielding effect is a repulsive force on the outermost energy level electrons of an atom due to the repulsion by the inner electrons. Read this again. Shielding effect is a repulsive force on the outermost energy electrons. I'll write outermost energy level electrons. And I can read the sentence again. Shielding effect is a repulsive force on the outermost energy level electrons of an atom due to the repulsion by the inner electrons. I don't think it's difficult to understand. There is a force, repulsive force on the outermost energy levels due to inner electrons, and that's called shielding effect. We'll go to sodium now. Sodium has 3 energy levels. So I'll write sodium over here. It has 1 energy level, 2nd energy level, and this is a 3rd energy level. No, only 3 energy levels. Now I'll try to compare sodium with lithium. But if I take it a bit closer so I can explain easily. You know, sodium has 11 electrons. From these 11 electrons, 2 electrons go to the innermost energy level. I'll draw circles, dots actually, 1, 2. And should I use a different color? Yeah, then it's seen clearly. Yeah, it's very visible. 2nd energy level has 8 electrons. And in the outermost energy level, sodium has only 1 electron. Sodium has 11 protons. Now see, the attractive force by the nucleus on the outermost energy level. This is the outermost energy level. This outermost energy level is attracted to the nucleus because of 11 protons. But you can see, even though lithium has only 1 energy level with 2 electrons, sodium has 2 energy levels inner to the outermost energy level, and these two together contain 10 electrons. Again, going back to lithium. Lithium outermost electron is pushed outwards by only 2 inner electrons. But when it comes to sodium, sodium outermost electron, sodium and lithium are both in the same group in the periodic table, group 1. They both have outermost electron 1 each. And in sodium, the repulsive force due to inner electron is very much greater than lithium, because this repulsive force is coming due to 10 inner electrons, but in lithium, only 2 electrons. So you must remember, when the number of energy levels increase inside, number of electrons also increase. Okay, when the number of energy levels increase, number of electrons also increase. When the number of electrons increase, the repulsive force on the outermost energy level electrons increases. It means the attraction of the nucleus on the outermost energy level electron decreases when you go from lithium to sodium to potassium. I have not drawn simply down the group. When you move down the group, the number of energy levels increase. When the number of energy levels increase, the number of electrons inside also increase. So when the number of inner electrons increase, the repulsive force acting on the outermost energy level increases. Now this is down the group. I took earlier lithium and beryllium. Lithium and beryllium, they are in the same period. For the same period, I said, because number of energy levels are the same, repulsive force is the same. But when you go down, because number of energy levels increase, repulsive force increase. So that I can write in 2 sentences in this manner. If I start with the shielding effect again, shielding effect is a repulsive force on the outermost energy level electrons of an atom due to the repulsion by the inner electrons. Across a given period, the number of energy levels remains the same. As a result, the shielding effect remains the same. Now, however, moving down a group, the number of energy levels increases. The number of inner electrons also increase when the number of energy levels increases. As a result, the shielding effect increases. The effective nuclear charge decreases. I did not discuss about the effective nuclear charge, but I can come to this and explain after the discussion of this given in the theory. We'll go to this shielding effect. This phenomenon, the shielding effect, is discussed as a force which acts on the outermost energy level electrons of an atom by the inner electrons. It's a repulsive force I have not mentioned here. When there are electrons between the nucleus and the outermost electrons, in addition to the nucleus attraction on the outermost electrons, they also experience an outwards force due to the repulsion of inner energy level electrons of atoms on them. Now see, outermost electrons experience 2 forces, one inside due to nucleus, one outwards due to shielding effect, which is the repulsion by inner electrons. The latter is referred to as a shielding effect. What is the latter? Outwards force due to repulsion of inner energy level electrons is called the shielding effect. When there are more electrons or more energy levels inner to the outermost energy level, there is high shielding effect. That's what I was explaining in detail earlier. One diagram I have just sketched over here. Here, the nucleus has 3 protons. This is lithium. Inner energy level, the first energy level has 2 electrons. And then there's 1 electron in the outermost energy level. Now see F1. This F1 is an outwards repulsive force due to the inner energy level 2 electrons. And there's F2. It is an attractive force on the outermost energy level by the nucleus. Let me see this. F1 is an outwards force on an outer electron due to the repulsion by inner electron, and that's called shielding effect. Now F2 is an attractive force by the nucleus on the outermost electrons. Now somewhere here I have written effective nuclear charge is F2 minus F1. You should understand the meaning of effective nuclear charge. Now, effective nuclear charge is this. Even though the nucleus is giving up an attraction of F2 force on the electron atomos, it is experiencing some outwards outwards repulsion also. The difference is called the effective nuclear charge. Effective nuclear charge is always lesser or smaller than the actual nuclear charge. Okay, effective nuclear charge is always lesser than the actual the force towards the nucleus, because some of it is cut off by the shielding effect. We go to the next one. For example, moving down a group in the periodic table, energy levels increase. Therefore, the total inner electrons also increase. Hence, shielding effect increases. Now you can see here, shielding effect is only due to 2 electrons in lithium. But in sodium, shielding effect is due to 10 electrons. There are 10 electrons in the first energy level and second energy level. Because of this, the outer electrons are less attracted to the nucleus moving down a group. Accordingly, the ionization energy of elements decreases moving down a group as shown by the following diagram. See, period number increases. First ionization energy decreases. Maybe if the period number is 1 here, period number 1. Let me see, period number 1, yeah, period number 1, period number 2, period number 3, period number 4, period number 5. We can say first ionization energy. I think if you don't add something else into this doesn't make much sense. First ionization energy, I can write variation down a given group. That means now this diagram is true for maybe elements of the same group, lithium, sodium, potassium, likewise in the same group, or magnesium, calcium, likewise when you go down. So please insert this also if you have the note with you. First ionization energy variation down a given group. We can draw this diagram for group 1, group 2, group 3. No, this is only for one particular group. Of course, if you take for group, now if this is for group 1, for the group 2 also, you have the same pattern. So for the y axis, we have to get first ionization energy variation down a group. And down a group, first ionization energy decreases. I think you have understood this concept very well. Once shielding effect is done, I'll go to the next part. Next part is effective nuclear charge. Effective nuclear charge. If you see this diagram again, I'll take lithium and beryllium. Lithium has 2 energy levels. Lithium has 2 energy levels. Even beryllium has 2 energy levels. Let me increase this again. Okay. Lithium has 2 energy levels. Beryllium also. Lithium has 3 protons. Beryllium has 4 protons. The effective nuclear charge means this. I said earlier, the total attraction by the nucleus on the outermost energy level is not felt as it is by them sitting on the outermost energy level. Why? Because of the shielding effect. I told earlier that this lithium is getting a lithium nucleus electron, lithium outermost energy level electron is getting attracted towards the lithium with a force of 10 units. It is an actual force by lithium, but on this outermost electron, there's a repulsive force due to shielding effect due to 3 units of force. So what is the actual force of attraction experienced by the outermost electron in lithium? It is 10 by 3. It is 7. This 7 is the effective nuclear charge. Effective nuclear charge. It is actually the net charge. It's something like this. Now you are spending on a business 1 million. You are spending 1 million as a capital on a business. And towards the end of the month, you have an income. You have income of 2 million. Now, can you be happy thinking about this 2 million's return? Not return actually. 2 million you earn as an income. Now, is this 2 million the actual income, the net income? Even though you are getting 2 millions, you should not forget that you have spent 1 million initially on the capital. So when you get 2 millions, your net profit is actually 1 million. Actual income is 1 million. So this actual 1 million income is the effective income. Effective income and actual income are two different. Actual income is 2 million, but the effective income is 1 million. That 1 million we can say the net profit that we call effective profit. So on lithium also, even though the outermost electrons are attracted, outermost electron is attracted with some force, it feels some lesser amount, and that is called the effective nuclear charge. So again, remember, effective nuclear charge is always lesser than the actual nuclear charge. So we go to this. Because of the shielding effect discussed above, the outermost electrons always experience an outwards force due to repulsion from inner electrons. Due to this, an outermost electron always feels a nuclear pull, which is lesser than the actual nuclear attraction. In other words, the force which is felt by outermost electron is a net force of the nuclear pull and the push of the shielding effect. Okay. Actually, this sentence is talking about the effective nuclear charge. Okay. This net nuclear attraction, which is felt by an outermost electron, is named as effective nuclear charge. I'm explaining this here. The effective nuclear charge increases across the period as discussed below for the period 2 in the periodic table. Now see, elements are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Because they are in the same period 2, they all have 2 energy levels. They all have 2 energy levels. You know, configuration of lithium is 2-1, O-level method, beryllium 2-2, boron 2-3, likewise carbon 2-4, nitrogen 2-5, 2-6, 2-7, 2-8. Because because shielding effect is due to inner electrons, always inner electron number is 2. So shielding effect is the same. Shielding effect is the same. But proton number increases. Because proton number increases, what happens to effective nuclear charge across the period from lithium to neon? Effective nuclear charge has to increase. That means nuclear pull will increase. But shielding effect remains the same. So therefore, atomic size from lithium to beryllium to boron to carbon to nitrogen to oxygen to fluorine to neon, it has to decrease because of increasing effective nuclear charge. So here we say across the period, proton number increases. Remember these points. Across the period, proton number increases. New electrons are added to the same energy levels. That means shielding effect remains the same. Hence, increasing proton number increases the effective nuclear charge. Therefore, electrons are attracted towards the nucleus more and more across the period. Thus, increase in the energy for the removal of an outermost electron. In other words, ionization energy increases. Do you get it? Across the period, the size of atom decreases. Therefore, the distance between outermost energy level and the nucleus decreases, and nuclear attraction on the outermost energy level increases. Removal of electrons become more and more difficult across a period. Okay, now based on this effective nuclear charge and shielding effect, we can talk about the ionization energy values, the effect of shielding effect and effective nuclear charge on the ionization energy. And why do we discuss this effective nuclear charge and the shielding effect? Because with the help of these two, we can talk about why different atoms have different ionization energy values. And if we know this idea very well, we can talk about the availability of energy levels in an atom. So remember, ionization energy is evidence that we use to show or prove the availability of electrons in energy levels and further in subenergy levels also.